and this is my master thesis presentation with the title Design and Implementation of a Scalable Wi-Fi Onboarding Protocol. Now, as we all know, the smart home adoption is advancing and therefore the number of consumer IoT devices is increasing rapidly. There are 25.44 billion IoT devices projected for the year 2030. And as we all know, IoT devices usually have a small form factor and therefore they do not have a user interface, which makes onboarding these devices a real problem. Therefore, manufacturers chose the Wi-Fi over Wi-Fi approach, in which the IoT device creates a temporary access point, and the user has to use the smartphone to connect to this temporary access point and enter the real Wi-Fi credentials. Clearly, this process doesn't scale well, because typically one has to download a vendor-specific application and the user still has to manually type in the Wi-Fi credentials. And therefore, the Wi-Fi Alliance introduced the Wi-Fi Easy Connect protocol in 2018, which aims at making the onboarding process easier because the user doesn't have to manually type in the Wi-Fi password. And enrolling a new IoT device is a three-step process. So first, the user has to use the smartphone to scan a QR code on the access point, which contains the Wi-Fi credentials. In the next step, the user has to use the smartphone to scan the QR code on the IoT device, which usually contains some cryptographic keys to encrypt the Wi-Fi password. And it's also sent to the IoT devices via Bluetooth or Wi-Fi. And in the last step, these devices are able to decrypt the credentials and connect to the Wi-Fi access point using the Wi-Fi credentials. But clearly, the Wi-Fi Easy Connect protocol doesn't provide scalability because devices still have to be added one after another. So what are the problems of the state-of-the-art protocols? So as we've seen, first, the IoT devices require vendor-specific applications. Therefore, users have to download the vendor-specific app and manually type in the Wi-Fi password. Second, the installer isn't necessarily the end user. Although most protocols assume that the installer is the end user, this is not the case in large-scale scenarios in which one would probably hire a contractor to install the IoT devices. And therefore, most protocols do not support these large-scale scenarios. Third, the protocols do not support remote onboarding. Protocols usually require a smartphone to transfer the Wi-Fi credentials, and therefore the smartphone has to be in physical proximity. And therefore, remote onboarding without being in physical proximity is usually not supported. And fourth, the onboarding after physical installation isn't possible because usually a button has to be pressed, which makes onboarding IoT devices at a later time very difficult because devices are usually installed in hard-to-reach locations. For example, a sensor under the ceiling can't be reached that easily. So now let's come to the general protocol idea and the protocol design. The general protocol idea was to use a private and public key for authentication and a almost unique UUID4 as the broadcast ID for advertisement. As we can see on the right side here, the commissioner and the IoT device are in possession of the same broadcast ID and are in possession of the public key and the private key respectively. Now, the first step here is that the commissioner sends the broadcast ID to the access point, which then uses this broadcast ID to advertise the network using this broadcast ID. Once an IoT device finds this broadcast ID, it tries to connect to the access point and uses its public key, its its private key for authentication. So the advantages here are that the access point can advertise multiple IoT devices simultaneously, which provides scalability. Another advantage is the mutual authentication. Due to the usage of the private and public key, we have an advanced security for the IoT device and the commissioner. And the last advantage here is that no third device is required in physical proximity, because the IoT devices can find the right network based on the broadcast ID, which therefore enables the desired remote scenario. Now let's talk about the entities in the protocol. First, on the left side of the graphic, we have the manufacturer and the retailer, which are responsible for installing the information on the IoT device and distribute these to the commissioner at a later point. The commissioner can be considered the owner or the operator of the network infrastructure. He's responsible for adding information to the network server using the app. The network server, on the other hand, is responsible for hosting a database, a AAA server, and updating the access points with broadcast IDs. The access points have to fetch the broadcast ID from the network server and use these IDs to advertise the network in the Wi-Fi beacons. The IoT device then has to analyze Wi-Fi beacons and join the network if it contains its own broadcast ID, and use the pre-installed credentials to authenticate itself. Now let's talk about the implementation. I did a prototype implementation using a Raspberry Pi 4B Plus as the IoT device, since it has an internal Wi-Fi card, and I use an external Wi-Fi card for the monitoring capabilities, because by default the Raspberry Pi doesn't support analyzing Wi-Fi beacons. I used an Intel NUC as the access point, since it has a built-in Wi-Fi card to host a Wi-Fi network, and a Google Cloud virtual machine as the network server, as it has a public IP address and is remotely accessible. I implemented the commissioner as an iPhone app, since it is a realistic scenario and it was very easy to set up a prototype using Swift UI. During the whole setup, I used a VLAN to make the whole setup process easier, since the Raspberry Pis aren't connected to the network via Wi-Fi at the installation time. Therefore, I used an Ethernet cable to set up the Raspberry Pi. Now, I want to present you a live demo of the whole prototype, which is basically just the iPhone app and how easy it is to add a new device. Now, I want to make clear that the Raspberry Pis and the whole network are somewhere else, so I'm not in physical proximity, and this is a demonstration of the remote onboarding scenario. So over here we can see the Wi-Fi pairing app, and over here we have the credentials file, which just contains the broadcast ID, the description of the device, and the private key. Now, if we just drag over this file in the simulator, it automatically opens the app using the corresponding app. The credentials using the corresponding app, because it knows the file type. And now we can see that the device was already accepted a few seconds after, so we can see the difference here. The device was added 8 seconds ago, and the last status change was 2 seconds, so it took 6 seconds to onboard the device remotely.